I'm Annemieke, and this is the e-learning for PLAST2bCLEANED on Key Exploitable Results 1 and 2. Number 1 is on a novel way to do polymer recycling, which is based on dissolution of the polymer. And Key Exploitable Result 2 is about removing antimony and bromine from that polymer solution and be able to recycle both fractions as well. So as I said, I'm Annemieke. You also see Sebastian Reinhardt from Fraunhofer ICT. He's a scientist on separation technology and is involved in PLAST2bCLEANED in that sense.
Yeah, hello everyone, and I'm here with Annemieke van der Rundstraat, who's a project manager and a team leader of the team that is working on the main process development of PLAST2bCLEANED.
So first I want to explain what is dissolution. So dissolution is a way where we use a low boiling solvent above its boiling point. So you create pressure, then we dissolve the target polymer from the plastic. Thereby we release the additives, so we can remove the additives from the polymer and then recover the polymer. You see on the left, let's say some graphic representation of what the dissolution. So on the top, the A and the B, so the polymer and the additive, dissolution, and then separation to the polymer and the additive. The main benefits of this process is that it's very energy efficient. It has a high potential for high quality polymers, so we get polymer retention, value retention, and we can recover the additives as well for recycling. And that's exactly what we do in PLAST2bCLEANED. We recover 3 fractions: the antimony trioxide, the polymer, and bromine additives. So this is the complete dissolution-based process that we developed in PLAST2bCLEANED. So now I will have some details on the dissolution. So what we did is dissolve the polymer. And what we saw is that the polymer isn't changed during dissolution. The chain length is not affected by the process, as you can see on the right in the graph. Some of the bromine flame retardants dissolve, and the antimony trioxide isn't dissolved and is then suspended in the solution. And from the trials on real plastic waste, electronics waste, we found out at a kilogram scale that about 2% is a total insoluble fraction. And you see a picture of that below. So it can be aluminum foil, paper, metals, anything from the first coarse filtration of the solution. So and then to the next step, where we recover the antimony trioxide. The antimony trioxide, as I said, will not dissolve, so there will be particles suspended. And due to the high density of the antimony trioxide, it will sediment from the solution. You see some pictures below on where the particles deposit on the bottom. But since there are small particles, it's quite slow. So what we did is look at different options for removal, except for just weight. So we added centrifugation or decanter centrifuge to be able to increase the speed of the settling of the antimony trioxide. In any case, we could separate the particles from the solution quite good. And these are results on a model material which we call the reference substrate. So that's a model for electronics waste. So then we end up with a solution where we have still the bromine, flame retardants, and the polymer in. So what we do is remove the bromine flame retardants using hot filtration. You see a graph of what a polymer can do. So the bigger molecules are retained on one side in the retentate, and in the permeate, the smaller molecules will pass through the membrane. And on the right, you see some examples of the molecules that are used in as from bromine flame retardants, and on the bottom one, that's a polymer. So you see the difference in size. So you can separate the two based on size. To put it into practice, so you see on the left a picture of the dissolution vessel. And if you look, you see the grayish color inside, so that's the polymer solution. And on the right, you see the permeate, so what's going through the membrane. And you have also an example of what you can then recover from that permeate solution of the bromine fraction. So now we have a clean ABS. So now we want to recover the ABS from the solution, from the solvent. That's so we have to remove the solvent. One of the things that you see is that when you remove the solvent from the polymer, the viscosity goes up quite significantly. So if you do it, in a normal way, the solvent will be encapsulated in the polymer particles, so you can't remove them. So if you just put it in an oven, it will not remove all the solvents. Also, adding vacuum will not help as it is encapsulated. So what we developed in the PLAST2bCLEANED is spray drying as an alternative. So here you see a graphic representation of what you can do with spray drying. So you can remove over 99.9% of the solvent. On the left, you see that's 98% is solvent with about 10% of polymer. In the spray drying, you recover the majority of the solvent, and you end up with only 0.6% of solvent. And by devolatilization extrusion, you can remove more solvent by applying also vacuum during extrusion, which is known technology, and then you can reduce the solvent content to below 1000 ppm, which is the requirement for polymers. So this is the overview again of the whole process. You have an idea of the different steps that we took to develop the process for PLAST2bCLEANED, and Sebastian will now take you into more details of fractions that we recovered.
Thank you, Annemieke. So what you can see on the slide right now is basically the whole process scheme that we developed, which Annemieke presented before with the dissolution, coarse filtration, centrifugation, hot filtration, and spray drying. As you can see, we have 3 output fractions, which is the ATO fraction, the recovered ABS, and the bromine flame retardant fraction. When we look at the antimony trioxide fraction, which we were testing to start with the reference substrate, as Annemieke pointed out, we received quite a good result with a fraction that had 90% antimony trioxide and a bromine content lower than 0.1%. When we look more closely into the recovered ABS, the residual solvent content is very important. It was below 0.5%. The antimony trioxide content was below the detection limit, and the bromine content was reduced by up to 95%. And when you look at the bromine fraction itself, you can see it's a very high bromine content fraction. Here we have 469,000 ppm of bromine, which basically means 47% of the whole sample is bromine. So here you can see we achieved quite a good result already on reference substrate, but obviously we want to work on the real material, and that's what we did next. And when you look at the real waste fractions, again, we recovered 3 waste fractions. And here I mainly want to mention the recovered ABS, which even has a residual solvent content of less than 0.2%. Again, the antimony content is below the detection limit, and the bromine reduction is still quite high with -73%. And when you look at the bromine fraction that we receive, well, the appearance obviously is a lot different because it's a more complex mixture with the real waste. Nonetheless, you can see with a 37% bromine content that it's a very rich bromine fraction that can be further utilized in the recycling facility in Terneuzen by our partner ICL, for example. To summarize our key exploitable results, the PLAST2bCLEANED project partners led by TNO and Fraunhofer ICT developed this novel technology, which includes, first of all, a choice of solvent and a successful dissolution method for the waste plastics, and then an antimony trioxide separation technology, which led to a high purity ATO on the reference samples, a bromine flame retardant filtration technology, which removed up to 95% of bromine on the reference samples and 73% of bromine on the real waste samples. And we also developed a technique to remove over 99.9% of the solvent in one step, which is a spray drying step, leading to a desirable dryness for the reuse of recycled ABS. And this technology within the project was started at the technology readiness level of 3 and was further scaled up to TRL 5 in kilogram scale within the project.
Which is then presented in Key Exploitable Result number 4. So we have an open access, or actually Sebastian is on his premises now, open access facility. So stay tuned for the e-learning on that facility.
And if you have any further questions, don't hesitate to contact any of the involved people mentioned below. Thank you for your attention. Goodbye.
Thank you.